Okay. So hello. Hello to the next seminar. And today our speaker is Katarzyna Kruszynska from our institution. Is going to tell us about the exciting new catalog from Gaia, as well as Gaia Space Alerts in the hunt for the galactic black holes. Kasia, please.
Hello, everyone. It's nice to meet you in a virtual way. I'm Katarzyna Kruszynska. For those who don't know me, I'm a PhD student at University of Warsaw. My advisor is Łukasz Wyrzykowski. And as Łukasz introduced me, today I will be talking about the hunt for black holes observed by Gaia. So I divided this talk into 6 parts. First 3 are introduction to black holes, what we know and what we don't know, to gravitational microlensing. However, I will cut that a little bit short since last week Shuda Mao gave a wonderful introduction to the topic. And I will talk a bit about Gaia. Then I will move on to the gist of the talk, which is Gaia and observed microlensing, and how can we, what are the methods that we are using for constraining the masses and the distance to figure out if we are observing a black hole or not. And then finally, I will talk a little bit about the future. So first of all, black holes and other remnants are mysterious objects that we don't really know much about. There are many questions that we would like to have answered. First of all, where are such black holes? Are they located in the galactic disk or galactic bulge, or maybe in galactic halo? The current running theory is that they do not occupy galactic bulge, but then again, we don't really have that much data on it. Secondly, what is the mass distribution of these remnants? If the constraints on the mass for white dwarfs and neutron stars is quite well described by the theory and their equations of states. Well, or the maximum mass that they can achieve before they implode. However, it is not very well known for black holes. So, and then again, there is something called the mass gap, which theorists say that between the maximum mass of the neutron star and the lowest known mass for black holes, there should be a mass gap. So there should be no objects observed of such mass. However, observations are either are against or not this theory, and that depends. So that's another question that we don't have an answer for. Thirdly, there's a question of natal kicks. The velocity of the natal kicks of remnants. Is it large or is it small? What's the most common velocity for neutron stars? We have some idea that from the observations of from pulsars, that solitary pulsars that are flying through the Milky Way, we have some idea what's their what their velocity is like and what's the natal kicks should be. However, we don't really know that for black holes, since we don't. It's very, very hard to observe a solitary black hole. And our source of knowledge for now are, we have 3 main channels. The first and largest one right now is the Lygover merger rates. So if we have a binary system of two remnants, then at some point they will merge and produce a gravitational wave. However, it comes with, well, we can only say something about them if they're a binary system. So there has to be a binary system of remnants, and it has to survive throughout the evolution. So that's one bias. Another way of another channel of knowledge about black holes are X-ray binary systems, where we have a black hole, which is or another remnant, which is well, consuming, accreting the mass from its companion. However, then we have to have a binary system again, which are not that common, and the binary system had to survive the event which produced the black hole. So there's another constraint. The third channel are non-interacting objects. However, most of those objects have been ruled out, and currently only one object has survived, which is actually a mass gap object. So it's the constraint mass of this object is between well, the most massive neutron star, which is usually around 2.5 up to 3 solar masses, and and 5 solar masses where we expect the black holes to begin. So as I said, all these 3 channels of knowledge come with their own biases, and what is interesting for us, so microlensing, well, it doesn't require a binary system, so it could provide new information that we were not privy to yet. So now I will introduce gravitational microlensing. However, I will be very short because, well, Shudamal talked about it just last week. For those who need a little reminder, gravitational microlensing is an effect of general relativity. When a massive object passes in front of a distant star, the star usually belongs to our galaxy or to its neighborhood, for example, Magellanic Clouds. And this causes the shift in the apparent position of the star, which is manifested by the change, well, by the change of the image of the star. It gets deformed and split into 2 images usually, or more. However, usually for microlensing, we cannot really, it's very, very hard, usually with modern instruments, not well, almost impossible to resolve these, to resolve these deformed images. However, we see the change in the brightness of during when the event is occurring. What is very important for microlensing is that the object which is passing, causing the event, and which is passing in front of the background star doesn't have to emit light. So it can be well, pretty much anything that we can have in our galaxy. So for example, it can be a planet, it can be a white dwarf, a neutron star, a black hole, and it can be a star with a planetary system. This is an animation. I hope it views correctly. If not, then I will go to the link created by Chris Rybicki, which shows basically how maybe now I will go in here. Which shows how on the top panel how the deformed images produced. So the blue oblong objects are the images, and on the bottom panel we see the change in the brightness. That's a standard microlensing event when we have a single source, single lens, and we can approximate both source and the lens as point objects. Let's go back to the presentation. Did I manage to do that? I did not. There we go. So gravitational microlensing, well, I'll give a short rundown of history. Gravitational microlensing was an effect of general relativity. So obviously Albert Einstein had to thought about it a little bit. And there is a historical record in his notes that he was actually thinking about it for a while, long before the first paper about it was published. However, he decided not to pursue this idea and returned it only in 1936, when at the beginning of the year, a Czech migrant approached Einstein, who was at the time professor at University of at Princeton, and this amateur whose name was Rudy Mandl. Had some interesting ideas about, well, different things, among them microlensing, and this caused Einstein to rethink his approach. And this work was finalized by the end of 1936 with the paper. And here on the bottom panel, on the image, that's I think that's one of the only photos that I have found of Rudy Mandl, and he was. As you can see, an amateur astronomer, because normally he worked as a dishwasher. Einstein, however, in his paper in 1936, noted that gravitational microlensing is a very rare very rare event, and that with the instruments and the technology at the time, it was practically impossible to observe. So he kind of discarded this effect. This meant that the idea and the method was lying dormant for many years, and the theoretical groundwork was only explored in the 60s by Liebes and Revstal. However, in 1986, Bogdan Paczynski revived the idea for this for this method, because he had a very brilliant idea at the time to use gravitational microlensing to find elusive object called machos. So at the time, there were, well, still are, there were two competing theories that would explain why the rotational curve of the Milky Way and other galaxies is flat. So the problem is that there is a missing mass that should cause the flattening of the rotational curve of the Milky Way. However, we don't see it. And the two competing theories at the time were WIMPs, so weakly interactive massive particles that do not belong to the standard model, and machos, which were massive compact halo objects. So basically machos were, the theory was that in the halo of our galaxy there were a lot of machos that were flying around. And Bogdan Paczynski's idea was to take a telescope, a larger one maybe, and for a long period of time look at Magellanic clouds to check if we see microlensing events that would be caused by such machos. This kickstarted a lot of microlensing surveys, and some of them are still working up until this day, with OAUW being a prominent example. And as for the machos, they were initially proved to exist by the macho group. However, soon, a few years later, they were ruled out first by Eros and then completely ruled out by OAUW team. However, in that time, it was quickly found that gravitational microlensing maybe will not find those elusive objects called machos, because probably they don't exist, most likely. However, it was quickly proved to be a very useful tool for search for planets in the exoplanets, basically. Especially because, as it was mentioned last week, the gravitational microlensing is very sensitive for cold Neptunes, And so far we have found, I think, well, I've checked the numbers a few weeks ago. So far we have confirmed 120 exoplanets found by microlensing. However, there is a future mission of NASA called Nancy Grace Roman Space Telescope, which is supposed to provide hundreds of such microlensed planets. Another uses of microlensing is, well, obviously, if we don't really have to observe, if we are not looking for objects which are emitting light, we can still try to find black holes, however, maybe not in the galactic halo, but in our own galaxy, well, closer to us in our galaxy. And if we have a lot of events, a lot of microlensing events, we can measure something called optical depth for microlensing, and this allows us to analyze and test the theories about the structure of our galaxy. And finally, oh, okay, sorry. So first I will talk about the microlensing. So there are very, well, microlensing events occur in very different shapes and sizes. The most common one is the single microlensing event shown here on this first panel. This occurs when we can, well, we have single lens, single source, and we can both approximate them by points. They're point-like. However, we can have a binary microlensing event, which can be caused by a well, binary system of stars. So the lens is a binary system. And then we will have different peaks and valleys. And the analysis of such event is very, very complicated, with, well, Gaia 16 AYE being one of the most complicated events ever observed. And another, well, another type of microlensing events is when we have well, our microlensing event, well, it has a binary system, however, not as a lens, but as a source. And here's an example of such event. So for this event, there were two possibilities tested, whether or not it's caused by a binary lens or a binary source, and the binary source seemed to be more likely. Next, obviously, if, as I said before, microlensing is great for looking for exoplanets. So we can have a planetary event which usually looks like this small blimp in here, or maybe not, sometimes it's more complicated. And if we have a long event, or we have if event is long enough, or we have observatories located in different places, then we have, well, we have to take something into account called the parallax effect. That's an example of such effect. Or if we, or if the source size of the source is comparatively large to the size of the Einstein radius of the lens, then we have to take into account something called finite source effect. Obviously, that's not all of the well, effects that we can have in microlensing. However, those are well, like most important ones, or more common. And I will talk briefly more about parallax effect, because this is the effect that I am studying the most. So parallax effect occurs when we have a long event, and the event is well, occurs for a long time. The period of time where the event occurs is so long that we have to take into account the movement of Earth, because it gets reflected around the sun, because it gets reflected in the light curve. Or if our observatory is located in the space, or we have densely covered light curve, and our observatories are located, well, one observatory is located in the space and one observatory is on Earth, then we have something called the space parallax. So we also have to take that into account. Or if we have a very densely covered light curve and we are observing our event from different locations on the Earth, then we can also sometimes be able to see the discrepancies between the star-dot model, and then we have to take into account something called terrestrial parallax. For well, for longer events, we either expect the lens to be more massive, or maybe it moves slowly. So it's hard to say using only the microlensing event data alone. However, if we have secondary effects or maybe additional data, we can try to measure something called microlensing parallax, as I said, from the parallax effect. And if we are lucky enough, from either we have a separate data set or something else, we can try to measure angular Einstein radius, theta e. And if we have those two values, then we can constrain the lens mass of the lens, which is very useful, and a very exciting result from a few days ago, published a few days ago officially, is the first solitary black hole which was detected using those two values basically. So it was a long duration event which occurred in 2011. It was followed up by a Hubble Space Telescope by two teams, and the photometric data allowed us to not us, the teams to measure the microlensing parallax, and the astrometric measurements of the done by HST allowed the teams to measure something, to measure the Einstein radius using the astrometric time series. And I will just show maybe briefly the animation. Oh, it's visible. So basically what they were hunting for in the astrometric time series is to measure the shift in the observed position of the star caused by microlensing event. I will explain that a little bit more later on, but I wanted to show that animation because I think it says the best what they were looking for. And depending on the which team you ask, it's either a 7 solar masses object with transverse space velocity of 45 kilometers, or 4.2 solar mass object with a smaller transverse space velocity. And both those papers are available on arXiv. So as I said before, for this event, the astrometric time series played a crucial role in determining the mass of the lens, and that's why Gaia is important for microlensing. So before and black holes, before I will move on to talk to explain more how we can use Gaia, I will first have to introduce Gaia. Probably a lot of you know most of the stuff that I'm talking about right now because of the public event yesterday connected to the publication of Data Reads 3. But just to give a short rundown, Gaia is a space observatory launched in 2013 from French Guiana, and it's a space mission of European Space Agency. It is located at the L2 point, which gives us the separation between Earth and Gaia of 1% of astronomical unit. Its main goal is to observe, precisely measure positions and velocities, movement of 1 billion sources in the Milky Way, and to create a 3D map of such sources. Of these sources, and the astrometric time series precision is going to be sub-milliarc second. The whole sky is covered from 440 to over 200 times over the 5 years period, and on average, one source is observed once every 30 days, which is good and bad. Well, it's usually bad for photometric catalogs. However, it is producing astrometric time series, which is very exciting, and for an amount of sources that is unprecedented so far. So far, Gaia data release has been one of them has been extremely successful, and has produced over 2,000 papers. However, yesterday I think I heard that data releases produce over 1,600 papers each year, or something along the lines. So that's very, very exciting. And well, instead of, as I usually say, that data release is coming very soon, the data release is here, and you can use the catalogs. Well, it's filled with a lot of interesting data that you can play with. Along the data releases, there's a second channel of data products that you can find connected to Gaia, and that's Gaia Science Alerts. It is publishing every week several transients, and it has been doing this ever since 2015, and right now it has published over 1,900 alerts. I think it now is closer to 19,000. 20,000 alerts. Most of these alerts are supernovae and novae, cataclysmic variables, young stellar objects, and so on. However, among all these events, we have found around 500 microlensing events since 2016. So as from Gaia's connection to microlensing, first of all, it's really great because unlike most of the ground-based, well, obviously, if they are ground-based, they cannot really observe the entire sky. So Gaia can observe the entire galaxy, and it provides data in 3-band photometry. So there's a white G band, and then a red and blue, not as white bands that we get from low resolution spectra. And those low resolution spectra are also quite interesting because we can, for example, use them for classification. And as I said before, it provides astrometric time series, which is very, very exciting. However, because of the constraints of the spacecraft that it was designed to maybe not look for microlensing events in general, but to achieve its main goals, Gaia has a very low cadence, and as I said before, one star is observed on average once every 30 days, and that's even lower for galactic bulge. So, well, that's quite of a problem. As I said earlier, microlensing has two counterparts. First is photometric, which, as I shown before, causes the brightening of the source star. And the second one is, and now I will escape the presentation and I'll go once again to the beautiful animations provided by Chris Rybicki. Where is it? Oh, I missed it, sorry. Here it is. It has also astrometric counterparts. So when our source is approaching the lens, the images get split into two. And normally we cannot see we cannot really resolve those two images. However, what we can observe with precise enough instruments, we can see the shift of the centroid of light. So the images are unequally brightened. One is dimmer and one is brighter. So this causes the shift of the centroid of light, and we can maybe once again we can see the deflection. And that's what that is what was observed by the two teams that used HST data for finding the first solitary black hole. Okay, back to the presentation and slide. Current slide. Oh no, sorry, my presentation broke down. Sorry for that. Gaia, strengths, weaknesses. Okay, now I will just start here. change. Okay. So as I said before, we have found around 500 microlensing events in the Gaia Science Alerts ever since 2016, and that's the map of these events. They're mostly located around galactic plane. There are some interesting events that we are not sure, maybe they are microlensing or maybe not. And the majority, well, the vast majority of the events obviously occur in galactic bulge because it's the densest area in terms of sky, in terms of star on the sky. There have been two major improvements to the detections rate of microlensing events over the years. The first of one of them has been around the middle of 2018, when Gaia has observed the Milky Way enough times, especially the galactic bulge enough times to provide us with enough baseline to actually see the be more sensitive for detecting microlensing events. And the second one occurred in the middle of 2019 when the new detector, sensitive for slowly evolving events, has been introduced into the transient detection pipeline of Gaia Science Alerts. And ever since that period, we've been steadily but surely growing the numbers of detected microlensing events. However, as I said before, finding a microlensing event by Gaia is one thing, but what can we do with the very patchy data? Usually not much. We might miss very interesting features. So for the events observed by Gaia Science Alerts, we use a follow-up network, which is to combine all the gathered data for the observed microlensing events, we use a service called Black Hole Town, and we work both with with the observatories within the Opticon network, Opticon RadioNet network. Well, we don't use radio, but yes, and then we also apply for time for various observatories, and even we work for even with amateur astronomers. And this is the map of all of the observatories we ever used, I think. I'm not sure. Well, it's probably not the most up to date, but as you can see, majority of the observatories that we have used are located in Europe, and then also Chile and other popular places. And our follow-up does not only consist of the photometric follow-up, we also do spectroscopy. We do it in two regimes. We use low-resolution spectroscopy on instruments such as LT-SPRAD or RSS SALT for classification. So sometimes, especially for the beginning of an event, we are not very sure if what we see is actually a microlensing event. It might be something else. So that's actually very useful. And high resolution spectroscopy that we do high resolution spectroscopy follow-up on the most interesting microlensing events, candidate microlensing events, in order to derive the source star parameters, or if we think that what we see is a source star mostly, because then we can get, for example, the distance to the source star, which we wouldn't be normally able to accurately constrain, especially if the event is occurring in the galactic disk. Here are some highlights gathered through the years using different types of tools. So we have high resolution and low resolution spectra here. The third thing that we use, before for example, we have an event, we are not very sure if it's an interesting event to pursue, and we don't really want to use our resources for spectroscopy. Then we can use archival data for early classification of such events. And this was a work conducted by Ilknur Gezer. as a primary leader, and this is used usually to rule out if what we are observing is an actual microlensing event, or maybe that's a common contaminant such as BE star or YSO. And finally, if we combine all of these things, if we rule out a contaminant, if we follow up an interesting event with a ground-based network, then we can catch very interesting events. For example, here's a gallery of interesting events from past few years, and as you can see, we can observe very different types of events. Some of them are highly magnified, some are not. Some have distinctive features and multiple peaks, and some don't. And that's a very interesting result. Okay, yes. So now I will move on to talk about a few very, very interesting events and the results that we had from Gaia Science Alerts. First of all is Gaia19dke, and normally, yeah, I will maybe go to the web page. Normally, I will not bore everyone with this event because it has been it's a binary event with a very, very distinctive light curve, as you can see. Maybe I will make this larger. However, what's the most exciting about Gaia19dke the most exciting recent result about Gaia19dke is that it is for this event we have received astrometric time series, and it was possible to measure the astrometric microlensing effect for this event. So this proves that Gaia is capable of providing additional information on microlensing events, and I think that's very exciting. Just to explain for people who are not very familiar with it, the most important panel is the bottom panel. Here in this gray area depicts the 3 sigma region of Gaia astrometry. The blue dots and lines represents the residuals of the astrometric model, which does not include microlensing effect, and the red dots and lines represent the model, astrometric model, which takes into account microlensing event. And if we look clearly and compare it with the upper panel, the largest discrepancies are between in the residuals between occur when there's the largest microlensing deflection effect occurring. So, for example, around caustic crossings. And here on the right-hand side is the on-sky trajectory of the source and the lens. Sorry, of the source. And this is the rotating caustic of Gaia19dke. And so the red line and black dots are the actual positions. Well, not the measurements, but where they should be. And the blue dashed line is the expected trajectory of the source if a microlensing event did not occur. Okay, let's go back. So that was a very, very exciting event. It was the analysis was conducted mostly by Chris Rybicki, and the results have been published as an image of the week a few months ago. Let's go. I'm sorry again, but my computer is not working with me today. Okay, we can start with BLD now. So Gaia19 BLD was another very interesting result, and I will switch to animation in a moment again. It was a microlensing event which was observed by multiple observatories, including Spitzer, because at the time it was still operational, and there was also data gathered by VLTI Pioneer, which is super exciting, and there was also a spectroscopic follow-up conducted. It was a microlensing event which had, because we had multiple observatories, and one of them was located very far away from Earth, such as Spitzer. Measuring microlensing parallax was quite easy, and then it also had a finite source effect depicted in here. And for this event, I will show a very cool animation, which again Chris Levitsky provided here, and it's really cool. So here at the top panel, we have the microlensing event occurring for Gaia in green, and then in Earth. Then in red, there's how it looks for Spitzer. And at a few moments in time, the animation gets stopped because it shows the images taken by VLTI. As you can see here, you can practically compare them with the upper panel. And these are the two kind of blended, but still somewhat resolvable two images, two different images, which were caused by microlensing. Okay. Now it's working. Okay, great. So that was Gaia 19 PLD, and now I will move to my own result, which is Gaia 18 CBF. It was an event which I personally analyzed. It was an event which lasted for almost around 1900 days, and it's the second longest microlensing event ever observed, at least in terms of the Einstein timescale. And it was also kind of problematic because it was very dim. So the baseline was in G close to 20.5 magnitudes, which means that we didn't have many tools available for follow-up. And the only available instrument that we had at the time was LCO, a telescope within the LCO network at Sighting Spring, which has 2 meters in diameter. For this event, I have found two solutions with microlensing parallax, and the time scale is between from 450 days up to 490 days around, and I have concluded that from 70 to almost 90% of the light is coming from the source star. So we have so for this event we were able to measure microlensing parallax. However, I don't have the access to the astrometric time series, obviously, because it's not public yet, and I couldn't use any other tools for it. So, but I really wanted to constrain the mass of the lens. So, what can we do? And this is a method which was used by my advisor and then refined by many authors over the years. So what we can do is we can take our microlensing parallax. Then, because our event was observed by Gaia, so then we can take proper motions from Gaia, which is great. And then we need to estimate this distance to the source. So, if we are lucky, we can try to, as I said before, we can try to conduct a spectroscopic follow-up of this event, and then using certain methods, we can derive the parameters of the source, especially the extinction and the distance to the source. But if we are not lucky or our event is very dim, as in this case, we can try to use archival data, and for this source, the distance to the source was conducted. We figured it out using archival data. Then we have to do a couple of assumptions. So first assumption is what is the galactic model? So where is the majority of the stars occurring? What's the density? What's the velocity distribution, and so on. And then, that's one thing that we have to assume. And the second thing is that we have to assume some type of mass function for remnants. Obviously, if we have if we think we are observing a star, then we can use, for example, the Krupa mass function. But for remnants, it's really unknown, to be honest. So we kind of do some hand waving. But if we take those assumptions into account and we take our data, we can do something. And actually, this provide as I said before, this method has been described in a couple of papers, and it has been refined and is still refined. We're still working on it. However, it's we can say quite a lot about our source, where it's located, and what's about the lens, and where is it located roughly, and what is its mass. However, the error bars are going to be large, depending on the type of data that we are ingesting. So these are the results for Gaia 18 CBF. It's either 2.65 solar mass or lens, or 1.71 lens. The distance is roughly the same for both solutions. However, as you can see here, the error bars are large. So it's kind of like the error bars are so large for both solutions that they are consistent with both white dwarf, a neutron star, a mass gap object, and the black hole. However, what is very important in here to note, this is the lens distance and lens mass distribution, but this panel is quite, the bottom panels are also very important. So the bottom plot is used to compare our results and figure out whether or not the light that we are observing from the lens is consistent, can be explained by is consistent with the expected brightness of a main sequence star. And we have two parameters here: lens light and blend light. Blend light is the observed light that we see in the light curve. So as I said before, from 70 to 90% of the light is coming from the lens. So basically, from the source. So the remaining 30 to 10% is depicted in here. However, the remaining 10 to 30% can be also explained by third light, for example, a different background star, not really a lens. And as you can see, and the lens light is the light of the main sequence star if at said distance, if at the expected mass. So we get our mass and distance from here, and then for this mass and distance we calculate the brightness of the main sequence star, and then we compare it to what we actually see. And as you can see, for this solution, most likely this is not a main sequence star. It's most likely consistent. Well, the majority of probability occurs in the remnant area, and it's slightly, and the main sequence star is slightly more probable for this solution. However, it's still not very popular. And for Gaia 18 CBF, we also had to test. Well, I had to test for different assumptions that that I have made. So first of all, I had to test whether or not my assumption for the main mass function of the remnant was actually good. And I tested outside of the assumed power spectrum that I have used, which was minus 1.75. I have also tested two other scenarios, -1 and -3, so less and more steep. And this also corresponds to, well, it basically the results are that for less steep mass function, we expect that the lens moves closer and gets more massive, and for the more steep mass function of the remnant, we expect that the mass gets smaller and the lens moves away, which is kind of makes sense. And then I also tested whether or not, because we used archival data for distance estimation, because we did not trust Baylor-Jones estimation of the distance, because for this source actually microlensing the parallax, the astrometric parallax measured for this source is negative in Gaia. Then, so I don't really trust the estimates provided by Baylor-Jones catalog for early data release 3 sources. And but well, maybe it's correct. So then I also tested that, and then the lens became a little bit more massive and moved a little bit closer. And all of these results can be read on arXiv. I provide the link here. However, today, finally, the paper got also published by Astronomy and Astrophysics. So it's also available there. Okay, and now the last part, and I have a few minutes left. So I'll maybe go slightly quickly through this. So usually it used to be the future, but now it's the present, because Gaia DR3 catalogs the data is public now, and within Gaia data release 3, there's one small catalog with microlensing events. These events consist of 363 microlensing events found in Gaia using 2 approaches. From July 2014 up until the May of 2017, so the time span of Gaia data release 3, and you can see well, you can explore this catalog now, and also corresponding to this catalog, there is a very nice paper, well, exciting and well, very interesting also, because it provides a very good exploration of the available data about this catalog, and it's available on our arXiv today. And it has also been accepted to ANA, but that's less important. The most important part is that you can actually read it. And finally, this catalog is available on well, various places where you can get your Gaia well, data. But I think the most popular and kind of useful for me is Gaia arXiv. And that's how the catalog looks like. And to the catalog, there's not only a paper, there's also a documentation. So, well, I encourage you to read the documentation as well. Here's the link to the, well, data model. However, maybe to the slides, I will also provide an additional section of the documentation with maybe some additional data which was not described in the paper. Well, with technical technicalities, which are not that important for the paper. Well, having our Gaia data release 3 catalog available, well, I wanted to do some additional analysis of this, of the microlensing events which are provided in there. And well, I wanted, basically what I wanted to do is to apply the same method as I used for Gaia 18 CBF to all, well, or maybe to the most interesting candidates from, well, microlensing events from that catalog. So what I did was, first I took Gaia microlensing, Gaia DR3 microlensing catalog, which is called Vari microlensing, and well, oh, I did not explain that. In this catalog, we provide two microlensing fits to the detected observed microlensing event. One is without blending, so we assume that 100% of the light in the event is coming from the source, and then the second one without constraint, without fixed blending. But what I did for this exploration, I took the microlensing events which had with fixed blending, so 100% of the light is coming from the lens, from the source. I selected those which had Einstein timescale larger than 50 days. And for these, I gathered all available data from other surveys, combined them, fixed blending, and then modeled them. And using some quick methods. And from these, I managed to select 34 most interesting events. And from these, depicted in here, finally, I have the selected, I have unfixed blending, and I have I have modeled them using all available data. And then I tried to find for which events I can actually say that, yes, this microlensing event has a measurable parallax, and it's better explained by a model which includes microlensing parallax. And this is depicted in here. Those are, I don't remember which number of events is depicted in here exactly, but from 12 to 19 events have measurable parallaxes, in my opinion. But that kind of depends on the criteria of acceptance. However, there's 2 or 3 events which should not appear in this plot, but maybe forget about this. And what I depicted also in here, I'm marked in different colors the type of events which have FSG. So FSG is the blending parameter for the source. So if it's larger than 0.7, it means that more than 70% of the light is coming from the source. So what we are looking for is a dim lens. And I have also depicted, marked a line for microlensing parallax. If we assume that the relative proper motion of source and lens is 4 milliarc seconds per year, and the mass of the lens is 4 solar masses. So basically, I was expecting maybe I will find something under this line, then it might be black holes. But unfortunately, because of the constraints of the catalog, probably we won't find. We will find fast black holes, but maybe not very long events. And this is an example of one such event found in Gaia Dataries 3 catalog. That's an event found also by 2 other surveys. Well, first I think it was reported by Assassin, and then also it was found in the catalog of the microlensing events occurring in disk fields of OAUW, which was produced by Przemek Mróz and others. And this is the light curve that I have managed to get for this event. And as you can see, the dashed line is the standard model, single Paczynski model without any additional effects, and it doesn't really match our data. And this is the result of the analysis that I have shown before for Gaia 18 CBF. And as you can see, it's most likely was, this event is not that very exciting because it's probably a star of mass around 0.8 solar masses. And what I want to do in the future is to do the same thing for all of the events in Gaia Science Alerts, and that will basically be my PhD thesis. So I will end here because I have been talking for an hour, and I will take questions now. Thank you.
Thank you very much. Feedback, and that first. And are there any questions? Or in Zoom?
Oh, yeah, maybe on the Zoom chat.
Right. So there's a lot of material.
Łukasz, I can barely hear you.
That's very interesting because I can hear myself.
Okay, sorry. So maybe I'll. Oh, I don't know what to do.
Anyway, I think I'm running out of time, so I'm going to stop here. So thank you very much, Kasia. Very talk and goodbye. And thank you all for joining. See you next semester. Thank you, Kasia.
Thank you. Okay.